through many classes and you're probably saturated, right? So I'm going to try and give you the essence of what this subject is without going too much into the deep mathematics of it. Okay? So I want you to stay with me and keep it interactive. Okay? So if at any point you feel like I'm going too fast or you don't understand something, just interrupt that all the time. Okay? So I'm going to deal with these three questions. Okay? What can change climate? What are the observed changes? And how do we know what changed? How did these observed changes occur? Okay? So these are the three things. So you've spent some time. What can change climate? You should know that, right? Okay? So let's hear what are the things that can affect climate. Greenhouse gas, solar, volcanic, aerosols, clouds are part of climate. So, right? So we're talking of what things that can be outside of your climate, in a sense. Because even though we get energy from the sun, it's considered outside. Even though volcano is on Earth, it's considered outside the climate system, right? Because it's not directly interacting with the climate and changing, right? Anything else? Anthropogenic emissions, so that includes CO2, other greenhouse gases, and aerosols, right? So, anything else? Plate tectonics, okay? Plate tectonics would be important in a long time scale. Yeah. Anything else? Land use, land cover change, right? So these are sort of the typical things that you all understand. Anything else that can happen on long time scales? Something like plate tectonics. Orbital variations, right? You know the astronomical parameters that affect solar radiation, like tilt, centricity, and precession. Okay, so we all understand that. I wanted to make sure we know the same kinds of things, right? Okay, so what can change climate? We're going to make it into two things. One we're going to call natural, right? So natural means it would happen even without you and me, right? So if none of us were on the planet, these things would still happen, right? So changes in sun, you have the sunspots cycle, right? You have solar cycles. You've heard of solar cycles? Okay, so you have variations in the sun, and if the sun is like your typical Indian voltage fluctuating bulb, it's going to affect the planet, right? So that is one thing. We've also seen what happens when you have a volcanic eruption. This is also a completely natural thing, connected with plate tectonics, but something that happens much more, right? So what happens when you have a volcanic eruption? So you have sulfates, what else? Carbon dioxide, dust, ash. So some of these will fall out immediately, right? And some of them will reach the stratosphere. If it's a large eruption, more of it will reach the stratosphere, right? And stay there for a couple of years, right? So while it is there, it is what's a volcano doing? Cools what? Cools what part of the atmosphere? The troposphere and the surface. But what would it do to the stratosphere? Okay, so we're going to look at what it does. And then we have orbital changes, right? These orbital changes include the eccentricity of that elliptic orbit. The tilt can vary between 22.5 and 24.5. And there's also the precession. Okay? So, precession will change what? What is precession anyway? So, even if you hold the tilt at 23.5, you can be tilted this way, or this way, or this way. So, when you change that tilt, the direction of the tilt with respect to the normal, what is it that will change?
It changes the phase facing the sun.
Phase. So essentially, if I'm pointing this way or that way, it will determine my summer and winter seasons, right? So if I flip it, I'm going to end up with summer season in January or so in the northern hemisphere and winter in June, July, August. Okay, so that gets it. So these are, of course, luckily not happening fast enough for you and me to notice. Otherwise, it would be like next year it's going to be summer now, so I don't have to be worried. Okay, and then there's something called internal variability. Okay, so this internal variability is sort of can anybody explain what internal variability means? What it means to you? So that is changes in the sun. So anything that has to do with changes in the solar thing is already covered. Changes in volcanoes already covered. Orbital changes taken care of. Yet there's something called internal variability. Okay? So if you've ever played with there's this thing where you have 4 or 5 pendulums, little balls, all hanging off the same thing. So if you let it go, one of the pendulums will come and all of them will start oscillating. So this is a very simple coil, right? But it's a highly nonlinear system. How those things, if you had a single pendulum, it would be a regular oscillating period. Suddenly, individual pendulums start behaving very chaotically. Okay? Now, the Earth's climate and weather system is a non-linear dynamic system. Okay? So, at its core, it is a non-linear dynamic system, which means it's got some chaotic order. Okay? So, something like an El Nino would happen if you didn't have changes in the sun, you didn't have volcanoes, or orbital changes. Just by the fact that it comes and goes every few years would happen naturally. Every few years your monsoon would be strong or weak. This is something that is a natural part of the Earth's climate system. Okay? Now it is a function of the dynamics. Okay? So this dynamics, we're going to lump it all into something called internal variability. Okay? So what that picture there is showing, can anybody tell me? So this is a picture from left side is November 97, right side is November 98. Do those dates mean anything to anybody? That's right. So this was the largest observed El Nino event, and that is after the El Nino is finished, and it's become a La Nina phase. So people know what El Nino, La Nina is? You've heard some? So that is a completely natural thing that occurs as a function of internal dynamics. It's a coupled ocean atmosphere dynamics issue. So these are all things that are occurring naturally. Alright? And then we're going to do the second part, which is anthropogenic. Right? So what is man-made and what is natural is something that we are distinguishing. Okay, so the first one is all greenhouse gases, right? And the second one we're going to say is all sorts of aerosols that we emit. You can emit from your power plant, cement plant, whatever fossil fuel you are burning. You can emit from your diesel truck or even CNG auto. You can emit from burning wood, firewood, or if any of you has been in Delhi in the last month, probably know that you can barely breathe because of all the burning of biomass. Okay, biomass being just leaves and twigs and wood, right? So all of this can produce substantial amounts of aerosols. And the last thing, which we've already discussed, is land use, land cover change. Okay? So most of what happens when you clear a forest, for example, or change something from vegetation, is that you end up changing the albedo of the surface, right? So this is a satellite picture, rows of fluorescent impact with rows cut out. So you can clearly see that there's a difference in the brightness of the surface in the vision, right? So this clearly will have effects on definitely the local climate and probably at the global level. Okay? So I've made you separate this up. What is natural, what's man-made? Why would we want to do that? Why should anybody want to separate what's natural, what's man? Okay, right? So if I have no control over what's natural, right? At least not yet, unless I start doing things with the sun, probably, or doing something to volcanoes, probably, right? So it's only this part that we have any control over. So let's now look at what the actual observed changes are, right? Yeah.
Are these demarcations very clear? Like, can the anthropogenic changes also not affect the El Nino land cycles? They don't interact.
They do. All of these things are all interlinked. So it's even thought that volcanoes trigger El Niños. That's even a theory out there, and there are people working on it. So it's not easy to separate them out in the actual dynamics of the problem, but it's a separation to be made in our minds as to what's natural, what's anthropogenic, right? So we see how we separate them in an actual situation. So this is, I don't know if any of you have seen these pictures recently. So this is from the latest IPCC report from the Summary for Policymakers. So this picture here is showing us what the annual average temperature anomaly is, okay, all the way from about 1850 when temperature records were really very, right? So you can see that it stayed flat and then it grows and then it's gone up again, right, in the last 40 years or so. So if you take just 10-year means, the decadal averages, you can see that there is some notion of an up and down and then an increase, okay? So there is, in both of these, you can tell that individual years go up and down, right? So there's some inter-annual variation. This is not a nice smooth curve, right? If it were a smooth curve, that basically means there's no inter-annual variation. Now you see ups and downs every year. That's indicative that each year is different from the other. Similarly, each decade seems to be different from the other. Sometimes you have a rising temperature, sometimes you have a falling, right? So variations exist, but then there seems to also be a trend. So you can look at the pattern of that trend spatially on the right. Right? So this is trend in degrees C over the whole period. Okay? So you can see that some regions are clearly showing larger temperature increases, right, than other portions. There are in fact some areas where you have a decrease. Okay, so it's not that the whole planet is warming at the same rate. Okay, there's a definite pattern to it. And so the headline messages are: each of the last 3 decades has been successively warmer. Okay, that's 3 decades right there. Okay, than any preceding decade since 1850. If you go back to 4 decades before, then there's in between, you can see some decade where the temperature was higher, right? In the northern hemisphere, 1983 to 2012 was likely the warmest 30-year period in the last 1,400 years. Okay? So clearly 1,400 years ago, you didn't have temperatures being measured using thermometers. But we all know about proxy data and how you can reconstruct temperatures from the past, right? Paleo data, you know. So there are also measured changes in precipitation or rainfall, mostly rainfall, but precipitation includes solid also, right? So this is over a 110-year period, and this is just the last 60 years, right? So if you look at the longer period, a lot of areas with blue, including our own, which indicate an increase in rainfall, right? But if you look at the last 60 years, there are large patches here where you actually have a decrease in precipitation. Okay? So again, there are some patterns that seem to come out as the observations come closer to the present day. So there are other parts of the system. So this is northern hemisphere spring snow cover. Spring would be the time of March, April, May in certain definitions. So why are we looking at spring snow cover and not winter snow cover or fall snow cover? Why spring?
Stable for the whole year. I mean, that is not going to that is not going to change at short period of time. I mean, if you take winter, there might be snowfall in the precipitation.
But it's going to melt in summer, right?
Yeah, after some time it will hit, but that will represent the snow cover for that year.
Why? This is my question. Why are we taking that as a
That's the maximum snow cover.
That is the maximum. So, if you've had a whole winter of accumulating snow, in the spring you have all of that still there, it hasn't started melting yet, right? That's when your melting processes start. So, your maximum would be attained in the spring. So if you look at the maximum snow cover area, that has been decreasing over time. If you look at Arctic summer sea ice extent, so this is in the Arctic Ocean where you don't have a landmass, it's just the Arctic Ocean surrounded by continents. So within that Arctic, you have lots of sea ice, and that area has also been falling steep. Okay? You can look at upper ocean heat content. Upper ocean means in the top 700 meters of the ocean. Okay? So this includes your mixed layer and all that. So within that 700 meters, there is a lot of buildup of heat. Okay? Now, some of this shows a lot of variation year to year. Something like sea level change does have variation, but it's a more steady change. Sea level increases steadily. So why would sea level increase? Thermal expansion, which is explained by this: if you put more heat into the ocean, water is going to expand, right? What else can change sea level? Ice melt. Which ice melt? It is not Arctic sea ice, it is land ice. Okay? You cannot melt sea ice and raise the water level because that's what Archimedes said you can't, right? So, okay, so we understand that we have, I mean, you're all familiar with the Keeling curve, right? You've seen what the CO2 concentration increases, so greenhouse gases have increased. Therefore, logically, you will expect a temperature to rise, surface temperature to rise. So there is evidence for surface temperature rising. You also expect that if you increase temperature, you're going to melt some snow and ice, right? Logical, physically consistent. If you melt some ice from land, it's going to go into the ocean. It's going to increase the sea level. If you put heat into the ocean, it's going to expand. So logical. So what's the big catch? There's no. I mean, all of this is fully physically logical and consistent, right? So what is missing here in the reasoning? Perfect? You all quiet? Fully? We should go home. Right? So, the question is, there are many questions. We see things vary, we see things go up and down. How do you know it is not part of some large cycle like this that goes like that? Do you know? Do you know that this is not going to go back up next year, or this is not going to go down next year? Because we were introduced to internal variability, right? Internal variability, the only example I gave you was El Nino, right? But then there are longer period variations. You all know of the ice ages, right? You know what an ice age is, what caused the ice age. You know the interglacial that we're in, and that we're going to go into another glacier. Hopefully, right? So, this is just part of some natural cycle. Okay? How do I know that this change in this or this or this is anything but within a natural range of change? I have no evidence so far, right? I have not looked at that in that sense. It could be just part of some cycle. The other thing is that just because I went to a movie and spent all my money buying the ticket and eating all the cheesy nachos and popcorn or whatever, doesn't mean that's why I became poor, right? Maybe I did all that and there was a pickpocket who took away my wallet, and that's why I don't have any money, right? So there could be multiple causes for the same effect. Just because temperature increase doesn't mean, oh, it is CO2. I can have the same kind of temperature increase, global average temperature, by increasing solar radiation, right? I can increase that thermostat on the sun a little bit, and maybe I'll get the same temperature. So far, we haven't seen anything to contradict that. So, what we're going to do is examine everything that has changed. Okay? So, first we saw temperature record, CIs, all of those changes, but all of those changes are driven by a whole combination of what are called radiative forces, right? You all know what a radiative force is. What is radiative force? Change in energy, solar energy. So, if your balance at the top of the atmosphere is changed, okay, if you're trapping more heat, then you will tend to warm the system. So that would be a positive forcing on the system, right? If I emit more by reflecting more light, for example, more of the solar radiation, then I will be cooling the planet by, okay, affecting the balance at the top of the atmosphere, right? So, we've seen all the various things, like if I have greenhouse gases, CO2, methane, hydrocarbons, nitrous oxide. So each of these has been emitted over the course of human history, right? Which, for practical purposes, are going to be just the period of after the Industrial Revolution, right? Even before that, things changed. Clearly, things like land use, land cover changed long back. Okay, the first farming communities had to clear land. and they affected things. But in terms of really increasing anything, it's post-industrial era. So these are all the well-mixed greenhouse gases. Then there are short-lived gases like carbon monoxide, non-methane volatile organic compounds, and NOx, right? So these are all trace elements, trace gases that come and go, but they become something else. CO will become CO2, right? And many of the non-methane volatile organics will eventually end up as CO2 or whatever else. So, but while they are in that phase, they have different radiative properties than when they become CO2. So each of these has had some cumulative effect in terms of how much they have affected the radiation at the top of the earth. Okay? So that is given in terms of watts per meter squared. So it's radiative forcing is always relative to some time. And in this case, it's 1750. Okay? So clearly the biggest part on this chart is CO2. Okay? So almost 1.7 plus minus something, right? So then there are other things that seem to have sort of negative values. So this vertical line here is a zero line. Then there are things that are showing as a negative radiative forcing. What is a negative radiative forcing? Something that will end up cooling the planet. Something, say for example, the ones here are all aerosol related. Okay? So you can have black carbon plantings which warm, but you can have sulfates, organic carbon, things that end up cooling the planet. Okay? So between the ones that warm and ones that cool, it's sort of a more negative effect or negative radiative forcing from aerosols. But then they also affect clouds, right? So that is not very well known, so you have this large uncertainty. Then there's also albedo change due to land use, and that happens to be a negative number. Okay? So if you clear land and change land cover, typically increased albedo means you're going to reflect back more solar radiation, which means you can cool or reduce the temperature, right? So, and then there's one last thing here. So all of these, all the way from CO2 to aerosols to albedo, from land use, these are all anthropogenic. Okay? And then there are what are called changes in solar radiance, which is the only natural thing listed there. So, you see that it is a small, very small number. It's about estimated to be about 0.05. Okay? As opposed to this, which is nearly 2. Okay? So, there's orders of magnitude difference here. So, these are, if you were to look at the radiative forcing change from 1750 in the year 1950, it was about a half a watt per meter square. By 1980, it was 1.25. And in 2011, it's about 2.3. Okay? So, in 200 years, we had put in enough radiative forcing to be about half a watt per meter square. Okay? So in the last 60 years though, we've said that's not enough, let's increase it, and we've gone, nearly 2 watts per meter squared more than that. Okay? So there's a rate of increase of anthropogenic radiative forcing that is very fast. Okay? So notice that I have not included what happens when you have volcanoes, right? Because volcanoes are episodic. They erupt, they put the aerosols up there, in a couple of years, it's all gone. Okay? So during the time that the aerosols are up there, they will directly affect the radiation. But if you take over a long period of time, that's gone back to zero. So it does not add to the cumulative. Okay? Fine? So the question really for all of us is, just because there are changes in anthropogenic radiative forcing, does it mean that changes in observed climate are all due to the anthropogenic factors? Why can't we say it's all natural? Okay? So that really is, how do we know that anthropogenic causes are responsible? Because unless you can say anthropogenic causes are responsible, you can't do anything about it. If everything is natural, then you just go about doing whatever you want to do. Burn whatever fossil fuel you want to do, clear whatever land, doesn't matter to the climate, right? It's all just natural. But if it is anthropogenic, then you're going to have to address it. So that's where we come to detection and attribution. Okay? So I've taken 40 minutes of your time just to define what my talk is going to be about. But, so detection and attribution, first thing I'm going to do is say what detection is. Okay? So it's the process of demonstrating that climate has changed in some defined statistical sets. Okay? So, if it was all just part of some cycle, what change you notice would not be considered a departure from your normal state. Okay? So, if I measure my body temperature and it says 102, right? Then I know I have a fever, right? So, because why do I know it's a fever and something is not right? Why do I know? Because there is a notion of a normal body temperature. Okay? That notion of what a normal body temperature is based on some statistics, right? Okay, so you have some basic statistical background temperature that all human beings are set. Okay? So if I know that, and then I measure 100 or 102, then I am detecting something is changed, right? Then I'm going to define attribution. Okay? So knowing that I have a fever doesn't tell me why, right? It just tells me something is out of normal, okay? There may be your family doctor who can look at you and tell you how you have this, but that is a rare part, or it is a rare quack who can do that, okay? So what would you do in order to say what the cause of the fever is? Or what do doctors do? The other symptoms, right? Okay, so I have a whole bunch of other symptoms. I have body ache, I have this, I have that. If you get to be my age, those symptoms will be every day. Okay, so how can the doctor make sense? What would the doctor do?
Thermometer.
Thermometer has already been used. That's how the fever was. What else? Tests. Yeah. So some blood tests, some X-ray, some CT scan, something, so that you pinpoint cause for, right? So that is the process. Attribution is the process of establishing the most likely causes of the detected change with some confidence. Okay? Now, if CT scan, X-ray, blood test, they're still not clear, there are situations where the doctor will have to do something else. They say, okay, I'm not sure, it could be this, it could be that, so maybe more tests, but in the meanwhile, that test will take 3 days to come, so I'm going to start you on this. So there's a level of confidence that is involved. Or it could be that the first test itself told the doctor exactly what was wrong, and that's a high level of confidence in your attribution, right? So, this is a very simple sounding thing. So, if I showed you a graph like this, right, there are 2 curves, there's a black, and then there's a sort of an orange one, right? So, they're both temperature anomalies. Okay? So, without telling you what the black one is, do you think these curves are different? Yeah? How would you say they are different? Can you describe in a qualitative sense what the differences are? Temperature trend? Is that what you said? Okay, so there's some sort of an increase in the temperature, right? In the red one. Whereas in the black one, you just have sort of a steady oscillating about some mean, right? There's no sort of increase you can tell. So, this is sort of a noise in a sense, okay? Whereas this one actually has, to your naked eye, a detectable change, okay? And it's easy to do some statistical test, right? Simple statistical test to figure out if these two have different distributions, right? So, for example, I can say, I'm going to take the slope of that curve, of that red curve, and see if that slope exists in the black curve. Okay? Can I spot that kind of an increased trend, or that level of the trend? Because what can happen? I can find the slope here, even at the red curve, which is a negative trend. Okay? So the red curve itself is a combination of positive and negative trends. To you, it looks like from here to here it's an increase. But before that, there has been increase and decrease in this period. If you look at the black curve, you take a trend here, and it would be an increase. But if could take another trend here and it would really. So, even the trends will have a distribution, statistical distribution. So, the question is the trends in this over a certain period different from that distribution? Does it belong to that distribution of trends? Okay? So that is a simplistic way of describing how you can distinguish these two curves. So you have a defined statistical sense of how one curve is different from the other curve. Okay? So, but my attribution problem still exists. Okay? So, I have to try and run a CT scan, an X-ray equivalent on Earth, right? So, to find out exactly what happened, right? So, how do I do this? So, if I were to pose this problem to you in a sense, I'm going to give you an Earth without any human beings, right? Which is exactly the same otherwise. Same everything, same position in the orbit, same everything else. Something we're going to call undisturbed Earth. Now that will be my control, right? Then I'm going to give you the other Earth where all the lights are on, all the fans are on, all the ACs are on, right? So we can have these two and measure the temperatures on both these planets, right? That would be one way of finding out whether our activities, human activities with all the GHGs and the aerosols and everything else, will fundamentally drive the temperature like the red curve in the previous slide, or this one happens to be the black curve where nothing seems to change so drastically, okay? So happens that this red curve is actual temperature observation, okay? And black line is what we think would be the temperature variations on Earth if no anthropogenic activity happened. Okay? So how do we know this? We don't have another planet that we can directly compare with, so how would we do it? So this is where we get into modeling. Okay? So it so happens this is our control and perturb experiments, right? A control one where there's no human beings or their activities. Only the natural things like the orbital variation and the what else? Solar variations and internal variations and volcanoes. Right? So, if I have no such planet available, a sister planet, I have to use some model. So all of you know what climate models are, right? You've been told what a climate model is. I'm just going to say that it intends to model everything that's going on. Okay? Changes in solar output, changes in atmospheric composition and chemistry and aerosols and clouds, and so all of these processes have to be represented to whatever degree of accuracy you can afford, right? So you essentially put all your laws of physics that some chemistry and whatever biology you can involved in this, you do all your conservation equations essentially, put them into the model, which is essentially the planet broken down into individual layers and grid cells, right? So you solve for all these equations and you get a three-dimensional structure of the atmosphere and oceans, okay? So the advantage of having, and then you have to be able to represent some processes that include clouds and whatnot. So within grid cell, you are trying to say, oh, you know, my grid cell is too large, so I have to represent a cloud, so I have to do something. Yeah, it's an approximation, right? So there are many things about modeling which I will not go into in this talk. Okay? So, what is the advantage I have with a computer model? Right? Other than me being able to sit at my desk and not worry about going out into field work. Right? What else? What else can I? What's a computer model going to help me?
Quantifying, is it quantifying or whatever you want to be?
So, in order to quantify what the effect of something is, right? So, what are the effects that we are trying to quantify? So, if I say, okay, let me see how increasing CO2 affects the climate. So, into this computer model, I can just put some more CO2, right? And see what the new climate state will be, right? I can say, you know, I don't want to change CO2, I want to just put aerosols. Just the sulfate aerosols, I want to see what it does. Or I can say, I want to just give it a solar irradiance change like it's been seen. Just the natural changes in the solar irradiance, I want to give it. So you can actually say, you can add all the natural forces, volcano, the solar radiation, and internal variability, of course, is always there. So you can also include orbital changes. You can do all that and see if only the natural climate was allowed to evolve, how would it be? Or I can say, I'll only allow CO2 to change, only methane to change. So you can actually see what the change in climate would be if you did one thing at a time. You can isolate the effect of each of these. Okay? This you cannot do in the real Earth because you have an uncontrolled experiment, right? Only one lab, and that lab everybody is changing everything. No control, right? But in a computer model, it's a much more controlled setting where you can change one thing at a time. So, what we have is many such controlled experiments. Okay? Because I may create a model that's really terrible. How many of you have even written a computer program? Most of you, yeah? If you've written some computer program, did it work first time? You had to fix errors, bugs, everything you have to do, and even after that, somebody is not happy with the way your output looks, right? So imagine that happening in your computer climate model. Okay, so there are many people writing computer climate models around the world, and they have been writing it for 30, 40 years. And these are really complex computer programs based on complex physical and other processes. Okay, so they will have problems. They're not perfect, okay? They are not the real Earth. They are just a laboratory Earth. Okay? So you have to understand. So when I say, if I increase CO2, there are, let's say, all the people there that raised their hands, each of them had a computer model of the climate. Will everybody give the same answer? No. Okay? So, what the details of your climate model are will change what answer you get. But they should all be physically possible. Okay? You can't have somebody standing out in the sun and his body temperature fall. Right? You can't increase the solar irradiance and cool the planet. Okay? So it has to obey the general laws of physics. So his model, her model, whatever the model is, has to produce physically possible. So people have done lots of experiments. So there are what are called model intercomparison projects, where they basically say, okay, we're all going to make some, run the same tests on our model, okay? And things like what's called a pre-industrial control, okay? A pre-industrial control simulation would be this. I'm going to assume my climate is from before 1750, before the Industrial Revolution, which means CO2 levels are much lower, land cover looks different, so everything was before 1750, right? Whatever conditions were, and nothing is going to change. All prescribed. So this is going to give me sort of the basic state of the climate without too much human interference. Okay? The equivalent of that non-black time series that was, within some time. Then I'm going to do something called a historical experiment. Basically, once Industrial Revolution has happened, I'm going to increase atmospheric change the atmospheric composition, volcanoes, solar forcing, so all of these things that we know have happened. Okay? I've shown you that radiative forcing bar chart, right? So we're going to put all the time varying components from our emissions. How much CO2 was emitted each year, or what concentration was in each year, how much aerosol was emitted. So all of that you put in, and you run the model from 1850 onwards, right? So you have 150 years of climate. So this is our history, so that's why it's called historical climate. Okay? So this one sort of gives you, without human being, yeah.
So we put the exact conditions for 1950 or
this is also prescribed. They all have to put the same values of CO2. Okay? So if you know what the CO2 concentration was in each year, you can say this year use this CO2 concentration. So it's all prescribed.
I mean, that year is just the value. What is the criteria for taking 1850?
1850. This is just because it's only after 1850 that you have temperature measurements that you can actually compare it. And temperature was the first sort of measurement that was taken consistently across the globe. Temperature and pressure were the easy things to measure, and then rainfall. So this date is set because you have measurements to compare against. From 1750 onwards, you can run it. But 1750 to 1850, you really don't have observations that you can compare against. Okay? Okay. So then there's also something called ensemble. Basically, if I run my model once, I get one answer. If I change the starting point slightly, I will get a different answer. Okay? So this, how many of you run any models? Weather or something, weather model, anybody who's run any? 1, 2. Okay, so there's a few of you who actually use the model. So when you have a nonlinear dynamic system, it's chaotic. So slight change in the initial condition, and you will end up with slightly different outcome. Okay? So this is just a well understood mathematical, not very well understood, but well recognized mathematical concept or chaos, right? It's a nonlinear dynamical problem. So if I want to understand whether my answer is purely because of all these forcings that I have changed, or I could have changed my initial condition slightly and then got the same or different answers. So in order to check that, there are what are called ensembles.
So,
Yeah.
how do you get initial condition for like 1850?
So again, it is a partly educated guess, partly from. You cannot be exact, right? Even in forecasting weather, where an initial condition is really important, you will not know for sure that the condition, exact condition of the system. So the initial condition is not known exactly, which is why you sort of do an educated guess. So it's based on somewhat on observations and somewhat just starting the model. Okay, instead of starting in January, I will start it in December. So that would be itself a change in initial condition, right? At what point do you start the model, right? Yeah. So when you have an ocean connected to an atmosphere, what's the big difference between ocean and atmosphere? Density and heat capacity, right? So, so if I have an ocean with a large heat capacity, for that ocean to respond to any change, it's going to take a long time, right? So it is a heavy inertial system. In order to slow it down, or speed it up, I have to apply a lot more time in order to. So when I start a model, okay, whatever my initial conditions are, there are some conditions, and then I have some solar radiation, some concentration of greenhouse gas that is there. Now the model may not be in balance when it starts. So it has to oscillate about some state and eventually reach some steady state that is physically consistent with the boundary conditions, right? So that period that it takes for your model to reach that sort of equilibrium condition is what's spin. Okay? So if you have an ocean attached to an atmosphere, your spin-up time will be many centuries. If you don't have the ocean, you still have to do a little bit of spin-up, maybe a few months, few weeks, should be. Okay, so then you also have certain experiments where it gives you the kinds of questions that a detection and attribution exercise is looking for. So these are your CAT scans and X-rays and blood tests. Okay? So you're going to run the model with only natural forces from 1850, right? So from 1850, what has mostly changed appears to be the anthropogenic forces, but you're going to say, no, I don't want that. Give me only the volcanoes and the solar radiation changes, and let's see what the model produces. So that will be what is called natural only, right? And then you say, I want one where only the greenhouse gases have changed. No aerosols, no natural things like solar radiation or anything. Okay? And then I can also say, give me all the anthropogenic changes, which is aerosols, land use, greenhouse gas. So you can see how I will have a set of simulations where each one is being changed at a time. Okay? There's only greenhouse gas, only aerosol. So, what will that tell us? Okay? So, yeah.
Natural only for that particular force like exactly what like the way it is historical miscellaneous, everything is there. So only for natural, volcanic and solar radiation, which the name of the experiment
This one is called MAT, N-A-T, I think, or natural. I don't know it's called the natural only experiment. That's the full name of the experiment. How the file name and the female file is stored, I don't know. Yeah. So I can actually look at what happens with the natural only run and the historical run, where the difference is in the natural only run there is no human influence, and in the historical run you have natural and anthropogenic influences, right? So on top here is temperature change. Okay, so I'm going to, in the black line is observations. Okay, so that's the observed temperature record, right? This is the same curve we've seen before. And then we have natural forcing experiments from many models under coupled model intercomparison phase 3 and coupled model intercomparison phase 5. Okay? So, in the blue curve is CMIP 3 and in red is CMIP 5. So, if you have only natural forcing, your blue, red and black are all together till about 1960, right? At which point your observations is separated out, it's doing something else here, right? Something that your natural is not doing. There's also 2 dips in temperature. Can anybody tell me what that might be? Volcanic eruption. So, this is about 1990-91. The Mount Pinatubo volcanic eruption. And this is, I think, Achutarao. Okay, so you have large volcanic eruption, that's a naturally occurring thing that actually reduces surface temperature, and that is seen in the. Now, when you include natural and human forcing, what happens is your curves are all pretty much on top of each other, right? So there's actually on this screen, it's not very clearly visible. Can you see a sort of a shaded area here? There's a blue shading and there's an orange kind of shade. So you have many models. So each of them is going to have some incremental variability, right? So all of that is put as a cloud, okay? So there's a cloud of range of possible model outcomes, okay? And this red and blue color is just the average, okay? It's just an average. But if you look at the top one, even that cloud has separated from this, okay? So it's outside of that range of model outcomes, okay? So, now this is actually just in terms of a global mean, yeah.
Models have been calibrated to match the observation. So is it really a surprise that they are?
Why would the model be calibrated?
The models will have certain parameters. What is the basis based on which the parameters are chosen? They would have been calibrated to match some of the data.
So when you do an individual parameterization, that's true. Once you put everything together, how the whole global is going to follow, whether it will follow exactly that curve is, you can't calibrate it to that extent, because you have to also do other runs, remember. Your control simulation has to be steady because you cannot, there's no observations to match. Okay? So to answer your question, I'm going to show you something else. It's not just that some global mean agrees. Okay? So if I have just natural forcings, then the temperature trend in degree centigrade over the 1850 to 2010 sort of gives this pattern. Most of the colors are blue, mostly blue, indicating that if you had only natural forcings, you would have cooled in large parts of this planet. Okay? Now, this is what the observed trend looks like. Okay? So you can tell from, matching the pattern through lazy statistical way, that this is nothing like that. Right? Whereas if you include natural and human forcing, this is the pattern that the model simulates. Okay? So, I can point out many features that are not matching. But on the whole, in a broad sense, this is a much better fit to this, or a much better simulation of this than the natural forcing, right? So, what we're going to do is try and go beyond this, is this just an eyeball comparison of two plots and say, oh, this is a better one than that. Because that is not a rigorous statistical test, right? So you have to be able to test it properly. So you can actually look at what happens in different areas, because when you refer to calibrating your model to match observations, would you match all the observations of everything? There's no way to do it. So you would say, okay, as long as my global mean temperature matches. But then, when you start saying global land, global ocean, North America, South America, different parts of the globe, you still see where the natural variations would have taken you, where complete natural and anthropogenic changes take, right? So, in all these cases, there's a separation of the natural variations alone from the full combination of natural and anthropogenic. And also, observations seem to be better matching with the natural plus anthropogenic. Okay? So, this is where we have a set of experiments that allow us to investigate whether natural variations alone are going to reproduce the observations. The answer is no, right? To first order, that seems to be the case. So then, we'll come to what would be a typical detection and attribution study. Okay? So, this figure in the dots, colored dots, okay? Colors are also becoming redder over time, right? Basically indicating that the warming relative to some 1880 to 1920 period, okay? So this temperature anomaly is changing, right? Now if I have a set of experiments which are only natural change is only, I will get blue line, okay? So, as we saw in previous figures, up to about 1960, they seem to be all together. Post 1960, separation. Yeah? And there's also a thin orange line. How many of you can actually see it? Can you see it?
Yes.
Okay. So that thin orange line is using greenhouse, or let me correct that. It is anthropogenic forces. So it includes greenhouse gases, human emissions of greenhouse gases. Because there are natural sources also of greenhouse gases, right? Especially methane and CO2, there are natural sources. So if you just look at human emissions, GHGs and aerosols, if you include that, so this would be from what's called an anthro-only run, okay? That gives you this sort of orange line, okay? So far, this is the same message as before. So, now, what I am going to do, or actually this is a figure taken from the latest IPCC report, which by the way was released in its full final form yesterday. So I think all of you should download it and read it over the next 6 years, okay? Because that's how long it might take. So now I'm plotting the same figure, but in a different way, okay? So in the top thing, my x-axis was years, okay? So this is your typical time series way of plotting what the evolution of temperature is. Now instead of plotting it against time, what we've done here is essentially plotted against this orange curve. Okay? So the orange curve is giving me a measure of what is the temperature change because of human activity, right? So that became my x-axis. Okay? So because it is relative to some 1880 to 1920 period, if you look here, before 1880, it's negative, right? Right? You following that? Or you take an anomaly and where you would be less than the anomaly, where you would be more than the anomaly. Okay? So, if I plot it against that, that's when my orange line becomes a straight line. Essentially, that's all I'm doing is what was a curve, I'm making that independent variable. Okay? So, this is my axis, which I'm calling human-induced warming. So now, what you're seeing is each of these years, and this is why these dots are color-coded, you don't see any of the red dots over here, right? All the red dots, which are the high temperature ones, are associated with large human-induced warming on this curve, right? The other thing is that you look at this top thing here. Essentially, it's telling us in which year the human-induced warming, so it's 1800 or so, human-induced warming was 0, right? Because that's my relative to time. So that was a 0. 1960, it was still a small temperature change. Then 80, 90, 2000, 2010. So this human-induced warming has, this is just a 30-year period, whereas this much change took 100 years. Following that? Yeah? So this is, in a sense, what you're doing is you're projecting something that's your temperature change onto the human-induced warming. Okay? What we can do is also project it against this natural. Okay? I mean, to be fair, I should do that to see how much of an influence that has. Okay? So I am going to now project this observed temperature change both against anthropogenic and natural. So I'm going to do this two-dimensional projection. Okay? So which is why I'm going to give you one of these figures. Okay? So basically a 3D plot, right? So I have natural warming on one low axis, human-induced warming. So this is the orange curve and the blue curve, right? So this is the blue curve and that's the orange curve. And in the vertical axis now I have the observed warming, right? So that straight line, that orange line that was there in the previous one, right? So this was my slope of that human-induced warming. Now, because I have two projections, it becomes a plane, right? So I have this sort of a colored plane which is giving me, on one hand I have a gradient in one direction of 0.7 and in the other direction of 0.9. Okay? So this is, if I was looking at the previous figure, this is just this human-induced swarming that I projected against. That would be my slope or gradient there. If I do the same 2D plot as before, but against the blue curve, that would be mine. Okay, so what we do is we'll let this sink in, we'll refresh ourselves and see in half an hour where we'll pick it up from this point. Okay? Any questions? Okay. Of this? So, methodology is not easy to explain in 3 hours. I would I'm not going to even try. So this is how much I can explain methodology. Okay? Not everybody would know what EOF means or projection. So it's very hard. So I'm going to rather focus on it's not just doing one simple